Hello. So thank you very much for the invitation, Nahwa. And let me try to tell you in this talk a little bit what's going on in quantum computation around the world. But before that, I mean, this is such an applied talk, quantum computation, that I would like first to say something useless, which is what is a pleasure to learn the laws of quantum mechanics. It sounds a little bit crazy to say that, but you know, penetrating how nature works, it's unbelievable, and it's a fact that humans have only 1 century of knowledge of quantum mechanics. We only have 3 generations of humans that know quantum mechanics compared to 50,000 of Homo sapiens. So we are in the beginning. Whatever you think this is very advanced will look childish in a few years. So let me go ahead. So the first thing I would like to tell you is that you might have missed some of the news that were in the newspaper some time ago. For instance, this one. This is Hillary Clinton claiming that the threat of quantum computers deserves a Manhattan-like project to protect the states. It is mentioned explicitly in the piece of news that, in a way, quantum computation is a modern weapon, and obviously it's a modern weapon against cryptography. Or you may have seen the news that Europe has put €1 billion in the development of quantum technologies, and this is divided in 4 big pillars. One is quantum communication, that means quantum cryptography. The other is quantum computation. Next one is quantum simulation. We can have, let's say, less than quantum computation, yet very useful, like the analysis of materials. And quantum sensing or metrology. So a new generation of devices which use the laws of quantum physics at the ultimate level, at the atomic level. Or you may have checked the news about China, and this is out of proportion. Not only they connected 48 cities with trusted nodes using quantum cryptography, but in 2017, they launched satellites to deliver entangled pairs, quantum entangled correlations, so that then you can do quantum cryptography. Then, as you know, cannot be broken. It can be cut, but not broken. Okay? Or the investment in a city. FA city with the amount of money which is mentioned is 10 billion to 20 billion. So, as you see, something is going on. So what's going on? Well, the first answer is at very high level. What's going on is that humans are controlling nature at the level of atoms, at the level of single electrons, at the level of single photons. And this is simply a completely new level of technology. You can think of the first century of quantum mechanics as delivering a first set of tools like the laser, like the semiconductors for making this computer, for instance, or nuclear magnetic resonances of atomic clocks that produce the GPS technology. So, but those are using quantum mechanics in a very primitive way. They're using a lot of matter to do a few things. Now we are going to the refined level. We can control one by one the properties of the individual elements of matter. And this is a new level. So we can do new things. Now, at the detail level, the fact that we can control matter brings the opportunity that we can code information into matter. That seems a little bit crazy, okay? But it is a fact that an atom now becomes the unit of computation. And how will we make computations? We will use the laws of nature at that level. So we will make that atoms do interact with each other, and that will be a computation for us. So we are entering the field of quantum information. So we bring information at the quantum level. We are entering the big and enormous field of quantum computation. We can make computations with matter at the quantum level. Okay. So I try to emphasize that this is not a fashion. I've been in science for many, many years, and there are little fashions. There are now people work in this thing, work in another thing. Now work in string theory. Now they work in holography. Now they work in this other thing. This is not a fashion. Okay, this is a threshold. We are reaching a threshold of where we dominate matter. So let me then focus little by little. The first step is understanding that we can compute with quantum mechanics. And the idea goes back to 1930s when a church passed Turing, other people, Gödel, all these people set up the basics of information theory, in particular of computation. And they realized at that moment that making a computation needs necessarily doing physics. It's a physics transaction. It's not a theoretical artifact. There needs to be a transfer of energy at that level. This is why our phones heat up, okay, why they get warm, or why we spend money to do computations. So whatever computation is based on physics. It is in the 80s that suddenly Feynman, a famous physicist of the 20th century, said, so why do you use classical physics? So why don't we simply go down to the underlying level, which is quantum mechanics, and do computations? So why don't we bypass classical physics? And indeed, that idea was catch up in the community, and little by little people started to elaborate to the level we have nowadays. More precise, now we can codify the extension of a bit to what we call a quantum bit or qubit as a superposition state. This is a property of quantum mechanics. You may have not only the 0 and the 1, but you may have arbitrary superpositions of 0 and 1. The notation we use in physics is this crazy symbol, cat we call. It was introduced by Dirac, a famous physicist of the early 20th century. Simply says that this is a quantum state with a logical state that we call it 0. Could be 0 energy level compared to the first energy level of an ion, or could be polarization of a photon. The important thing is that you make the abstraction and you say 0 and 1 are now logical extensions of a bit, which is a qubit. And the fact that it's a theorem, it's not a theorem, it's actually a postulate of quantum mechanics that you may have superpositions of 0 and 1 that makes it completely different. It's an extension of whatever logic we have in classical computation goes to quantum level in a different way. Have we realized qubits in nature? Indeed, there are plenty. There are like 20 different versions of qubits that have been studied. One is to use photons, and now you codify information at the quantum level, for instance, in the polarization of the photon, or, more crazy, on the time of arrival of a photon. A photon may arrive now or later, and that can be considered a 0 and a 1 on the quantum level. We have produced qubits with trap ions, and the technology there is really to try to play with the internal levels of energy of one of the electrons that you have there. Or one which is becoming extremely fashionable, superconducting currents. And there you go down to amazingly low temperatures and you manage a superconducting current to be on superpositions of rotating clockwise or anti-clockwise. Seems almost magic. As they said, no, advanced technology is comparable to magic. Now, I will not be technical, but let me just write some very basic things like that. No need to understand the equations, just what I'm saying. It's a fact that now we manipulate these qubits with the laws of physics. That's the only thing I want to put here. So with a magnetic field acting on a qubit, I can do a 0 to become a 0 plus 1. That's it. Or, for instance, by letting the guys interact I can generate the basic gates that you need for the logic, like the control knot. As you see, some of the gates in quantum mechanics are identically logically to the gates that you have in the classical world, but there are other gates like this first gate, which is called Hadamard gate, which are not there. It's a fact that the implementation of physics, so the laws of physics, are delivering a new logic to manipulate the quantum bits. Now, why we believe this is relevant? Well, there are two amazing facts when you go to the quantum world. The first is that you have this superposition principle. So if you have one qubit, you can handle the superposition of 0 and 1. But if you have two qubits, you have the possibility to handle the superposition of 0, 0, 0, 1, 1, 0, 1, 1. If you have 3, then you have 0, 0, 0 up to 1, 1, 1. So 8, guys. If you have n, you have 2 to the n. So to give an example, I computed for you what is the requirement to write a quantum state on a classical computer of 53 qubits. Well, this is 2 to the 53 complex numbers. So you make the counting, and this is 10,000 terabytes. So 53 qubits are simply essentially impossible to describe on a classical computer. Okay? So it's a fact that you have exponential superposition of classical information in a single quantum state. I will repeat it. Take an ion trap, put there 50 ions, and describe that on your classical computer. You cannot do it. Okay? Not even describe it. Second, if I act on those, I simply send a laser to these guys, all of them will evolve, all this superposition will evolve, as if it were a massive parallel computer. So it turns out that a quantum computer can handle an amazing amount of information and can process it in parallel. So this is like an impressive jump of technology. Wow. So why don't we, what do we do? I mean, we should all be working on these quantum computers. Well, indeed, we are many of us, but there are drawbacks that are not mentioned very often, and I want to mention them here explicitly. It is false that anything can be done on a quantum computer using quantum logic. I give you examples that are very crazy. Multiply two numbers. Can I make a quantum computer a secret? Can I deliver a secret, which is a multiplier? So I put on 2 qubits the 2, and on the other 2 qubits I put the 3. Can I get the 6? I can make the 6, but I cannot make that this is a multiplier for any entry that I have on the registers. Why? Because these are the laws of nature, and at the microscopic level, the laws of nature are electromagnetism, quantum electromagnetism, and this is a theory that has inversion on time, so you can reverse every operation. So you have what we call unitarity, you can reverse things, and I cannot reverse that, because what would be the inverse of 6? How do I know it's 2, 3 or 1, 6? I couldn't know. There is an ambiguity. So that means that there is no way that nature will make a trivial multiplier. No way. What nature will do is something really peculiar. It will have to keep always memory of one of the two guys that are multiplying. So it is perfectly possible to have a machine that multiplies two numbers, provided that I keep one of them with me. So I can have the multiplication of xy into x and then x times y. This is the clue combined to the fact that x could be on superpositions to have what we call entanglement. Now, we are facing one of the difficulties of quantum computation. We have to be refined at the level of guaranteeing that entanglement will be preserved along the quantum computations. Another thing that you cannot do with a quantum computer is copying. For instance, imagine I want to copy 2 into a 0. So 0 is like a white paper. I want to copy 2 into 0. Can I add 2, 2? Well, not in general. And this is because there is a theorem that says no cloning. I'm not describing here. So I don't have the safe button on a quantum computer. Okay? Well, And finally, there is a postulate in quantum mechanics that says that when I measure, the result of the measurement is probabilistic. You have inherent randomness in nature. So we are forced to work with probabilities. So altogether, let me summarize. What are the benefits of quantum computation? You have exponential memory support. You have speed parallelization. And I didn't mention it, but you have a low energy consumption. So a supercomputer nowadays spends of the order of millions of dollars in energy. A quantum computer will spend less than $20,000 a year in energy, because you simply have to go to the regime where quantumness works. What are the cons of quantum computation? Well, it's a change of logic. So that is relevant. There is no way you take, it's not like learning Python. You cannot take students out of whatever engineering degree and say, okay, here you have a crash course on Python. That doesn't work like that. First, you have to learn the restrictions of quantum mechanics, the laws of quantum mechanics, and then you have to find out your way into these amazing quantum algorithms. And the technical challenges are also amazing. You have to have well-defined qubits. You have to have single addressability and readout of every qubit. You have to have coherence. You have to have a high fidelity for every gate. You have to have high fidelity for the secret. You have to scale this machine to something big so that you can address non-trivial problems. So this is the magic of quantum algorithms. I will give only you two, which I think are relevant for the crypto world. Okay, the first is what we call queries to an oracle. There are mathematics, there is computational sciences, there is this idea that I can't quantify the number of queries I need to find out something. So, for instance, I want to learn about the function f. So what I will do is that f, I'm trying to use the word oracle and the Delphos oracle in the old Greece. Well, I have to take my plane, I have to fly, I have to consult the oracle, and then I get a response and I come back. So you see, it costs money to consulting the oracle. So the question is, if I want to learn things about F, how many queries do I have to do? How many? And the question is, could I use quantum mechanics to send the queries as a superposition of queries? Can I do that? If so, can I learn something about F, my classical F, using quantum ideas in a more efficient way? Indeed, this is an amazing result by a guy called Grover. He showed that the extreme case, which is to find one guy in a complete database of n elements, well, classically, to have probability 1 of knowing this guy, to finding this guy, you need n queries, okay? N queries. Whereas in the quantum mechanic world, you can do it with a square root of n queries. So that means that, you know, when you would do 1,000,000 calls to the oracle, now you only have to do 1,000. What is a problem that can be addressed with this new idea? Well, hashing. Okay, hashing for bitcoins is a problem of finding a number. Okay, so that can be used. Grover's algorithm can be used against hashing. And you would get the square root of n. It's not an exponential increase. It's a square root only. The second problem is factorization. And then the question is, I give you a very large number. Can you give me the 2 prime factors? Well, what we do in quantum mechanics is not addressing naively this problem, but we address a related problem which is mapped polynomially to the factorization, which is finding the period of a function. So you have a number which is chosen randomly, a, and I have to find out what is the period, mod n. So what is r such that a to the r is equal to 1? It's a fact that there are all theorems from previous centuries that relate the 2 problems. If you know this period, automatically you can find out P and Q. So factoring is in the same class as finding a hidden period. Well, it was Shor who did that. Peter Shor, one of the great mathematicians alive nowadays, and he invented a secret that I depicted over there. that serves to find the period. What is relevant is that this circuit has an exponential advantage over the classical technology. So the field sieve technology that is the best we have nowadays needs exactly exponential of n 1/3 log n 2/3 to find out the two periods, whereas a quantum computer would need only n cube. So as you see, this is an exponential speed up. Okay. Well, so now you go back and you realize that sooner than later, a quantum computer will factor larger and larger numbers in an efficient way. So this put at risk all the technology based on RSA, well, the discrete logs, the elliptic curves, all these technologies can be addressed with a quantum computer because all of them can be mapped to a problem of finding a hidden period. Okay, so this is the big idea. We do have an algorithm. It's not that we have a quantum computer and we have to look for the algorithm. No, we do have the algorithm. So if we have the computer, we automatically run that thing. One of my students has implemented all the algorithm already, and we only need the quantum computer to run it. So it's not me who says these things. It's not Hillary Clinton. It's the NSA that says must act now. Okay, against the quantum computing threat. And not only that, but you may know that they have advised not to use a number of protocols, except the SHA 384 and some of them. All the others are de-recommended. They are mentioned to be not safe. And not only that, the NSA asked the NIST, the National Institute for Standards and Technology, to set up a competition for what are called quantum-resistant algorithms. Those are classical algorithms that would not be broken by a quantum computer. The call ended in 2017. There were 80-something candidates presented. The NIST asked the teams to collaborate and coordinate those that were on the same categories. And by now, some of them were proven to be not safe. And by now, there are only 26 alive as of the last time I learned about this. So it's still going on. And there will be 2 recommendations, one for signature, one for key distribution. I think, well, you may know how these things are going. So there are 2 ways to escape a quantum computer in the world of security. One is to build quantum-resistant classical algorithms. The other is to quantum cryptography. And that's a separate solution. Now, people ask very often when these things will happen. Well, the fast answer is it's happening. It's happening. We are building quantum computers. So in this sense, let me tell you what has been announced very, very recently. This is under the name of quantum supremacy. The basic idea, look at the time. The news are of September 23. I think today is October 15 or 14. So it's only 3 weeks ago. Okay. So Google announced, no, Google did not announce. There was, the paper was leaked and, everybody got it because you have these bots of Google sending information about what you are following, and that immediately come to all of us. And 1 hour later, it was stopped, but we got the paper. Okay, it's a long paper with a lot of details, and essentially there are 2 sentences I want you to remember about Google. One is 53 qubits. That's it. Remember that. And the second is first quantum computation that cannot be reproduced on a classical supercomputer. And let me qualify these 2 sentences in more detail. The first sentence says 53 qubits. So in more detail, they have made a chip that has the shape, it's exactly that chip, okay? With 54, one of them doesn't work. The one in white doesn't work. But the amazing idea that is new is that so far nobody had an idea how to stop the interactions between the qubits while you are not doing a quantum operation. You see, this is the laws of physics. So if I'm a charge positive and you're negative, we do interact. Whatever your boss likes it or not, you do interact. This is physics. So how do you manage two guys who are there not to interact? They are physical, so they do interact. So this is a problem called crosstalk. Nobody had a good idea how to stop it. But now Google had this idea, which I find it very remarkable. They put intermediate qubits, which are not coding any information, but they are putting a barrier, a physical barrier between the other two qubits. So they preserve the quantum state of every qubit, and only when they decrease that, they can interact. So this is a dramatic step forward in the elimination of one of the main problems in quantum computation. So good for Google. I think they did something good. Don't look at the plot, but at the numbers below. This is the error. Amazing. It's a factor, more than a factor of 10 reduction versus everybody else in the field. And not only that, but times of operations on the nanoseconds. Again, a dramatic step forward, because now you have only to eliminate the barrier. The interaction is instantaneous, essentially. Rather than talking to the two guys and making crazy things, you simply eliminate the barrier, they interact, puff, and you stop it again. Actually, the two-body interactions are only 12 nanoseconds, where the single one that you have to tune the directions is 25 nanoseconds, as compared to Google. And let me say, not only on isolation, but simultaneous. Can run on the 53 qubits, all of them operating on them, the error is the same. Amazing. This compared to the quoted error by IBM, which is between 1 and 5%, and the real error when you run experiments on IBM machines, well, this is orders of magnitude better. What they have done, I said, first, quantum computation that cannot be reproduced on a classical supercomputer. Exactly what do I mean by that? They have done something that you may consider naive, crazy, or completely out of any reason, which is they have made random circuits. Here is the random circuit, an example. Random gates, random. And that you program. You do these random numbers, random notation, randomly 1 and 3 qubit interact, and so on, random. You pass the same thing on a classical computer and you compute the output. And now you compare. You run one thing on the quantum computer, the other thing on a classical computer. You should get the distribution of readout. And now you compare. And what they have done is they have put to the extreme of the quantum machine, they have done 20 layers of operation with 1,000 single qubit gates and 400 2-qubit gates, essentially with depth 20 and 53 qubits. And these needs on a classical supercomputer would need 10,000 years to be computed. Remember, 2 to the 53 operations for all of them, and you have to do it 20 times 2 to the 53 by 2 to the 53, the matrices. They have run all of that on the best supercomputers in Germany, which are at Jülich, and they simply broke at 50. So 51, 52, and 53 are now purely quantum numbers. And what they have checked, if you do a random circuit, how do you know that it is a quantum result? Well, that is technical. I will go very fast. They have checked that the probability distribution obeys the laws of quantum mechanics or shows interference. If I had a laser, which I don't have, and I would point to the wall, you will see that when you look in detail, some of the points of the laser are very bright and some are not. So there is a speckle in the laser. This is because it's quantum interference. There is a destruction of probability. So when you do that, you should observe destruction of probability, and that's exactly what is called the Thomas-Porter distribution. So either you see that or you don't. And that's exactly what they have done. They have seen that the output is reproducible and shows quantum interference. They have quantified that in a number. It doesn't matter the number. It's a figure of merit invented for that, and it shows quantum supremacy. So you may ask, is this quantum supremacy useful? No. It's a random secret. Well, they claim this could be used to deliver random numbers, purely random numbers. But we have other techniques which are not that heavy to generate quantum numbers, random numbers. Is it impressive? I think it is very impressive. Okay, it will be remembered in years to come because we have really made the jump. This is the jump. That cannot be reproduced. Why is it not useful? Why? Well, because most of the problems we have, which are relevant, have structure. So if you want to solve a molecule, there is a structure there. And classical methods exploit this structure. That makes it more difficult for the quantum computer to be better than a classical computer. Now, what are we thinking now of doing with a quantum computer as a useful algorithm? We are thinking of doing the following. So far, we have two methods of doing algorithms. One is the one I mentioned before, gate circuits. Another is called annealing. The D-wave machine is using another technique, which is tunneling effect. But now we have another idea. Why don't we use variational techniques? What is this? Well, it's simply doing, I don't have the picture. It's simply taking a circuit like the random walk, but now adjusting every interaction and individual gate to minimize an optimization problem. So that is producing nowadays the first variational quantum algorithms, and they are now being used already typically for quantum chemistry, for machine learning, and little by little on finances. And there will be a plethora of variational algorithms. I'm just quoting here a number of them, variational quantum eigensolvers, autoencoder. These things now are only known by a few people, but in the next 10 years, there will be plenty of literature. And not only that, but we can now also do control of the experiment. So we optimize in our variational method, not only the gates, but even the pulses that we send to the computer. So we take the problem as a whole, and anything that can be optimized is optimized. Now, if you ask me, would, as a crypto community, feel in danger? Well, not today. Not today. Okay. Now, be careful. Okay, be careful. I thought 15 years ago that I would never see a quantum computer, and I'm giving a talk on the quantum computer that is already there. And it's quantum supremacy on top. So humans have a lot of ingenuity. So let me finish. My conclusion is very, very, very simple. It's not when, okay? Because as I said, it's happening now. So my question, it's a little bit a political issue. Quantum computation is not about when it's happening. It's about who. Who will do it, okay? And so my conclusion is that what is at stake is whether you have it or not, and I'm very, very happy to be here with my friends originally from Darmstadt and now from the Newborn Technology Innovation Institute at Abu Dhabi, that we are collaborating to construct a first quantum computer in the Emirates. And as I keep telling everybody, in a humble way, but in extremely clear, focus way of proceeding. So we will do it. We are collaborating with a number of institutions. We do have some experiments. What you will see eventually in Abu Dhabi is something like that. This is the one from IBM, but it's a commercial fridge. What you see on the right is a fridge. So this is only to manage that at the bottom you will have a point where you will have a temperature of 15 millikelvin, that is minus 273 Celsius. Why? Because there the laws of quantum mechanics are at full. Okay, that the world is quantum, no classical. The stages are just, you are cooling the system, and the difficulties are how you hardwire all these things. Think that the order of magnitudes of wire that now have to be sent are 500. And, you have to keep coherence every time. On the bottom, you have one qubit. You have never seen one of them. This is a qubit. This is a transmon. This is where you have these superconducting currents. Why there are this funny shape? Because this is the Josephson junction that makes the control of the qubit very precise. And we also have this supercomputer, which is in a church, Mare Nostrum. Why? Because this is the second largest computer in Europe, and the new generation will be the first. And we have whatever we do on the quantum world, we have to compare to the classical world. So the Institute will try to do basic research, of course, for academia, training, outreach, and applied research for corporations. And again, here you have more designs that are needed. So what's at stake is technological sovereignty, in my opinion. So let me thank you very much for your attention. I went a little bit too long.
Yeah, no problem at all. Thank you, Jose. Let's go straight to the slide of questions and see.
Yeah, the first is cryptography. Okay, so what people are working on now, the first contracts are coming from the chemical sector. So typically, what can you do for quantum chemistry? That implies new generations of drugs. Okay, let me make it clear. When you address the world of drugs, of medicine, humans have always proceeded in the same way, by trial and error. We simply try something, doesn't work, try something, doesn't work, try something, till something works. Penicillin was discovered randomly in a way, no? So the idea that the quantum computer can help is that we will have the opportunity to compute molecules. Not to try them, to compute them. And that's a jump. So we can try many other things because we are computing the shape of the molecule. Another field is artificial intelligence. You can combine quantum computation to train neural networks, but quite the opposite is better. Neural networks to train a quantum computer. We are working on this thing in particular. And another field, I'm mentioning three, okay, is finances, where people are trying to do the auction pricing and every operation which is very heavy computationally. Every night, you know, the huge banks have to perform a number of computations, Monte Carlo computations for their clients, whether we can speed up that by a dramatic factor. And we are also working on that. Sorry that I'm getting older and I don't see. Are you? Oh. Okay, so as I mentioned, Europe is trying to do a quantum computer under the umbrella of the flagship, and this is called Open SuperQ. It's completely behind what's going on in the corporate sector in the States, which is dominated now by Google and IBM. Microsoft is heavily behind, and there is another company called Rigetti, which is also behind. What I cannot tell you, because this is difficult to know, is what's going on in China. So we know that there are some things, but I cannot assess at what level they are. Okay? The private sector is ahead of the research of quantum computation, but not ahead in the field of quantum cryptography, which is now in the hands of universities. It is not ahead in the field of quantum sensors. This is still at the universities, neither of quantum simulation. The private sector has only put an enormous amount of money in quantum computation for the reasons which are obvious along the talk. Okay, so still universities play a relevant role in quantum technologies. I'm not saying in quantum computation, but definitely Google and IBM are far ahead from any other quantum computer in the world. I do think that that blind computation is absolutely relevant field. There are plenty of papers in academia now about blind computation. I think is a relevant field. Why? Because I do believe that in the next years, no, I don't expect, I may be wrong, but I don't expect to have a laptop which is a quantum machine. I don't think so, okay? Nobody has a clue how to make the technology to work at room temperature in a laptop. So it's very likely that the other thing will work is that you will be working on your problems and eventually will connect to a quantum computer as a quantum PU, no? A QPU, CPU, all the units you want for a specialized computation. So you have a CPU, you have a GPU, and now you will have a QPU, okay? And you would only ask a very heavy computation to the quantum computer, factor. You want to factor something. Now you rather want your computations to be blind, okay? So if you connect to the internet, you want the guy who is running the experiment not to know what he's computing, okay? So there are plenty of schemes now. There are plenty of people working on this thing because very many people see the idea that the quantum computer will be a common resource at some point that can be used by individuals, but very likely the computation will be critical for something. And a molecule, I give you an example. I mean, I'm investigating a given molecule for something, I find the solution. Probably the chemical company doesn't want to have anybody knowing what they are computing. So it's necessarily a big field around quantum computation and security. So I think this is it. So sorry for being too long.
No problem.
Thank you.
Can I have a big applause for José Ignacio Latorre? So without further ado, we'll go right through to the next speaker. What would a quantum computer do to crypto? By Najwa Araj. Please give her a big applause.
Thank you.